I'm Michael Killen. This is part 2 of an interview with Joe Stagner. He is the Executive Director of Sustainability and Energy Management of Stanford University. And from industry, I have heard there's a belief that he and Stanford have developed an energy, climate, heating, cooling system that is more advanced than any system of its type worldwide. In this interview, I want to find out, what are they talking about? And so that maybe we all can learn, and those who are in a position to take advantage of the leader will be able to do that. Before we get into the interview, I do want to mention that, as a lot of people know, I articulate, for example, California's climate plan, its goals and its strategies. And in this interview, I want to learn from Joe about his system, because goal number 3 of California's climate plan is to double the energy efficiency of existing buildings. And Stanford has clearly, from what I can determine, done that and is planning to do even more of it. So Joe, thank you again.
My pleasure, Michael.
For being here and sharing your thoughts with us. You heard me mention that I have to paint goal number 3 of California's plan next month, double the energy efficiency of existing buildings. How in the world somebody going to do that? I mean, some people say to me, Michael, a lot of the low-hanging fruit has already been automated with insulation, windows, and energy-efficient appliances. How are you going to get another? How are you going to double the savings now?
So I think one of the keys is realizing how buildings use energy. They use 3 kinds of energy: power for lighting and machines, cooling for air conditioning, as people call it, and heating for hot water and space heating. And so when you look at those 3 forms of energy and the way humans have used them thus far, you come to realize that cooling isn't really the delivery of cold, it's the collection of unwanted heat. So while you're delivering a system of heat to a building sometimes, when you cool it, you're actually taking heat away from a building. And thus far, society has been throwing that heat away. And what Stanford unlocked is we could take that heat and use it to meet the heating demands of the campus, a big portion of them, rather than throwing it away. So with heating, cooling, and power being about 1/3 each of building energy use, if you can now make use of 1/3 of that energy that you used to just throw away, that unlocks a whole new avenue of energy efficiency in buildings that, together with all the conventional energy efficiency things of insulation and windows and efficient equipment and lighting, allows us to get to that 50% goal.
Could you repeat something? Because for a moment my mind went somewhere. Let's see, a building is affected by the environment 3 different ways. One is, and step in if power is for lighting.
Lighting and operating machines, motors, electronics, computers, those kind of things.
And the operation of each one of those items creates heat.
Heating itself is the delivery of heat. Cooling is the taking away of heat. And power, when it's used, it turns into heat. So when you send electricity to a building, it all ends up as heat inside the building. When you run a light, you get the light, but then it turns into heat. When you're operating a computer, that electricity turns into heat. All of us know, the heat coming out of the back of the computer. Well, where's the energy for that heat coming from? It's the electricity that went into the machine in the first place. So all of the power and electricity that goes into buildings for various things, it's turned into heat after we use it.
So the next step in the process of doubling the energy efficiency savings of existing buildings is, as I think you've said, to take that heat as much as possible and to use it to create new, more electricity,
No,
No?
it's to use it to avoid using electricity or fossil fuel to make heat. So take an example where you're at home, and suppose it's hot outside in the summer in California's Central Valley, and you're air conditioning your house. Well, now somebody turns on the hot water spigot in your house to do laundry or to wash dishes or take a bath or shower. Well, what happens typically is natural gas starts flowing in your furnace, and you make hot water that flows through the pipes to your faucets. Well, at the same time, you're taking heat out of your house and exhausting out the side of your house through your condenser. And you ask yourself, why am I burning fossil fuel to make heat at the same time I'm throwing away heat out the side of my house? Could I just take that heat instead of throwing it away, make hot water with it, and then I wouldn't have to burn natural gas? Or if I had an electric heater, I wouldn't have to use electricity. So it's not that recovering waste heat makes electricity. It allows you to not use electricity or fossil fuel to make that heat.
Okay. So in a way, I was correct in part of what I said. You're going to take the heat that's being created in a building, and you're going to use it. You don't have to turn it into electricity.
Correct.
That's what
you're
you're
going to
saying.
use it productively to avoid using electricity. Same thing.
Yes. And how do you use that heat to cool a building?
Well, you're not using the heat to cool a building. Really, cooling the building is taking heat away from the building. So again, use your house example. You're in Phoenix, Arizona. It's 120 degrees outside, and you're using electricity to air condition your house. Now, suppose you need some hot water to do laundry, big old tank of hot water in your washing machine. You could burn natural gas to make that hot water through the conventional water heater, but if you had a heat pump that could take the heat that you're wasting from air conditioning, that you're sucking out of the house to cool it, and use that to heat up water instead of burning that natural gas, then you're avoiding using that fossil fuel just because you're reusing your waste heat. Or if you had an electric water heater, you'd avoid using electricity. So it's not that using the waste heat productively creates electricity, it saves a lot of electricity. That's why it's really an efficiency measure and why it would help with California's goals to make a building energy use 50% more efficient.
Okay, so a bottom line statement would be one of the most important new ways, although it's been going on for a while, but is to much more take advantage of the waste heat that is generated.
I think that's the single biggest thing we can do with buildings. I mean, most people know you can make your house more efficient, right? You can have more efficient refrigerators, better windows, better insulation. And people conventionally think that that's the solution to making buildings sustainable. Make them as efficient as you can through those measures, and then supply them with only green electricity. But in between the two is all this waste heat that we've been throwing away. That unlocks using a lot less electricity and certainly a lot less gas off the grid. And so that means overall the building's far more efficient because it's drawing less energy.
Now I think that's extremely valuable. Now, I have a home, 3 bedrooms. We have a central air conditioning system, a central heating. How practical is it for me to get a heat pump and put it in the backyard?
Well, it's completely practical, and it wouldn't be in your backyard. It'd be in your house where your furnace or air conditioner now is. They make them for the house. They have 2 kinds. One's called a reverse cycle chiller. You could Google it and find all kinds of units you could buy for your house. And the other's called a triple function geothermal heat pump. They're basically the same machine and the same kind of thing Stanford did on the big scale, in that they take the air conditioning they're doing for a house, and they take whatever that waste heat is that you might need for hot water, and they use it. They turn it into hot water for your house, and they only throw away what you don't need. Now in winter, when you're not air conditioning, how can these things heat your house? Well, they can suck heat out of the air. A lot of people are familiar with heat pumps from the old days that sucked heat out of the air. Even when it's 40 degrees outside, you can suck heat out of the air to warm your house with an electric heat pump.
Okay.
You could also suck it out of the ground. And that's the difference between the reverse cycle chiller and the triple function heat pump. Reverse cycle chiller sucks heat out of the air in winter, and the triple function heat pump sucks it out of the ground if you put one of those geothermal wells in.
So this is a question out of your area, because I know you work in the terms of a $500 million investment at Stanford. How much would it cost me to put a heat pump in and the other device you mentioned?
Sure. Heat pumps aren't very much more expensive than regular furnaces and air conditioners for houses. If you priced out a brand new furnace and air conditioning package for your house, a heat pump might only be 20, 30, 40% more. So they're not very different than your regular air conditioner. It's just instead of throwing all the heat out of the side, they're routing a little bit of it in another tube through a tank of water to heat it up. So they're not very much different in concept or size than a regular heater or air conditioner. So you'll find if you Google them, the prices are all, very normal to regular air conditioners, not really that much.
Oh, okay. Now, I don't see in the press, I don't see in the media, hardly, if any, discussion about using waste heat to improve the energy efficiency of the state, this country, a house, a campus. I don't see any literature. If I search for it yet, but it's not coming across my desk.
Right.
How come?
I think a lot of people just don't know about it. The way the energy systems in this country have evolved, we've taken the easiest road. We're extracting the fossil fuels, we're using simple machines to burn them. They're all very inefficient, but they were easy and cheap. But now that we have the technological challenge of doing things sustainably, people are having to search, and necessity is the mother of invention. They're trying to find, well, how can I do things more efficient? And just like us, once you start looking, the answers start to become obvious. You look at the total amount of energy that's being used, you say, wait a minute, I'm throwing a whole bunch of energy away through my air conditioning and I'm turning around and burning fossil fuel to make more. I could save a bundle of money if I just reuse that waste heat. And so there's not too many people that have started to think about this, but thank goodness for California and our regulations. They've said, look, I don't know how we're going to get there, but let's set a goal to do better. And when that goal trickles down to students and people like Stanford, they say, all right, somebody says let's try and get better, and we think we need to too. That's a good point. You start to think about it, and you start to find things and be innovative. That's what America and other places are great at, right? You start to solve a problem and you become innovative, and suddenly, doors get unlocked that you never even knew existed.
Okay. Now, how practical is it to think about, let's say, the city of Palo Alto, which is certainly a leader at trying to reduce greenhouse gases and increase energy efficiency. First of all, the city, can they put in one of these big district?
Certainly.
They can?
Yeah, so if you look at where there's a dense collection of buildings in the city, downtown, etc., they're great candidates for district energy. If you went and did a study and looked at how much energy they're using and did the same kind of analysis we did at Stanford, you would find that a district energy system would work just fine. And again, you could go all the way down to the single house and design things. So I think the technology's out there that over the life of the equipment, it's actually cheaper than the way we're doing things now, and it uses a lot less water and produces a lot less greenhouse gas. It's really a question of people understanding and knowing about the opportunity, and then realizing it's going to take time. Just like if you've bought a gas car and you're 1 year into it, it's hard to throw that away and get an electric car to be green and sustainable. But you can sure know, I'm going to keep this car for 3, 4, 5 years, and the next car I get, that's going to be the new one. Now that I know about electric cars, and now that they're going to be down in price and make sense, well, I'm going to get that electric car next time. I may not throw away my current car to do it. So when you look at the buildings in Palo Alto, old houses that have old equipment, you're like, hey, when you go to replace your air conditioner, how about putting a heat pump in instead of an air conditioner? Yeah. And so you slowly start to turn over all these facilities, and in maybe 10, 20, 30 years, you migrate more and more into this. I mean, how long does a home air conditioner last? 10, 20 years, yeah. People are replacing them. So in theory, you could turn over all the air conditioners in Palo Alto in 30 years if people were educated about it and they just went and did it.
Okay, that's very helpful to me. But tell me, what do I need, or our audience need to know? What building blocks of knowledge do we need to know to appreciate that Stanford may have built the most advanced system for capturing waste heat and using it in a way that it doesn't have to use more?
Sure. So two ways. The first way is we compare how much energy we use to heat and cool our buildings to the way we used to do it with a gas cogeneration plant. And those are all simple engineering calcs. You say how much electricity and natural gas in total do I consume to power, heat, and cool the campus with the old system, and how much am I using to do it with the new? And the new system uses less than half of what the old system did. So from straight energy efficiency calculations that engineers do, you know the efficiency of the system is twice as good because you're gobbling up only half the energy. And then when you calculate your greenhouse gases, you say, well, great, you're only using half the energy you have, but it's also now clean energy. And so that expands it even more. So with our new system, we cut our greenhouse gas by 50% because the new system was 50% more efficient. When we then switched from a greenhouse gas emitting fuel like gas to clean electricity, then we bumped up our greenhouse gas reduction from 50% to 68%. And looking to the future, as we green up the rest of our electricity, then we'll move to 85%. And as we start removing the rest of our gas vehicles on campus and going with all electric buses like we are with our Marguerites, people love the new electric buses, then we'll cut a few more emissions and we'll get to 90%. And then we find the little gas water heaters in small buildings around and replace them with electric ones supplied with clean power. We'll get a little bit more out. So we have a very clear path on how to be completely sustainable at Stanford in terms of energy and greenhouse gas. We're 3/4 of the way there and devising the programs and solutions that will get us to zero in the next decade or two, well before the IPCC 2050 goal.
Maybe I need some help with functions. Now, I met with someone from an organization, which you can pronounce the name better than me, EDF. Maybe you can pronounce it the way the French do?
Électricité de France.
Well, that's pretty easy.
Yeah.
All right. And I thought they said to me somewhat of the breakthrough or where you've pushed really forward was to take some of this waste heat and then apply it to the water systems of your building as well to create hot water. Maybe I didn't hear them correctly.
Yeah, I don't think it quite stated it right, but the other thing we learned when you switch from fossil fuel to clean electrification is that fossil fuel energy systems, the big commercial ones, they use a lot of water, a lot of drinking water. Any big power plant on the grid, they use a ton of water. That's why nuclear plants are next to oceans and lakes, because they need a lot of water to cool. So our cogen plant was using 25% of our campus drinking water. And it was because you use that water in evaporative cooling towers to discharge the heat that you don't want, the waste heat, to the atmosphere. When we started reusing that waste heat instead of throwing it away, well, then we stopped using all that drinking water to throw it away. And we saved 18% of our total water supply. So the benefits of going to clean electrification and reusing waste heat go far beyond energy, cost, and greenhouse gas. We found they save a ton of water too. So that's the energy-water nexus that we've uncovered.
That's the breakthrough.
That's one of the breakthroughs. That's one of the water breakthroughs, sure.
And are you interested in sharing that more of that knowledge, not necessarily here, but with other universities, with cities?
We have reached out for the last 5 years since we uncovered this opportunity and started designing the system and proving it would work, even well before we built it and operated it. We've been reaching out. We've talked at conferences, had papers published in magazines. I'm going to talk to the Big Ten and Friends Utility Conference in a few weeks out in the University of Nebraska. We've had the President's Council of Advisors on Science and Technology see our system and included in a write-up to President Obama that this was a good potential way to attack some of the nation's energy problems. Electricity to France, they're the world's largest electricity provider. They, the ambassador from France and the National Sustainability Committee from France, have come to see the system and understood France has got a great electric system. A lot of it's clean power.
Sure.
If we electrify, we can clean up our emissions, and it fits right into their strategy of having an electrified society.
Okay, so I just want to say, do you feel like you have succeeded right now in articulating how far you have pushed the technology that people can call you a leader?
I know we have the good story. We have lots of media and reports available, and we do a lot of outreach. But we do hear, even from people on campus, They didn't know how green Stanford had become. Others don't know this technology. It's surprisingly difficult to reach several billion people in the world, no matter how much you talk, no matter how many awards you get. We are reaching a lot, though. You know, we've got a lot of people. We've had over 10,000 people go through our plant. So we're working hard, but we've only touched, you know, just a few people in the total.
Sure. All right. So I feel right here in our setting, you have made your point.
Great.
Right. Got a question from a viewer, and he is the director of sustainability for Penn State.
Right.
And he's also the director of the Sustainable Institute. And his name is Paul Shrivastava.
Okay.
I may not be pronouncing it right.
All right.
All this pressure of all these cameras. And he asked, you know, Stanford has a lot of researchers, energy research, and others, has a lot of gifts here. And are you able to do anything with your knowledge to, in a positive way, affect California's climate change plan? And I guess he's referring to doubling the energy efficiency. Are you able to get your message to the state? Maybe he's asking that and getting the state to promote it. And
well, we're certainly trying. You know, both my group's direct units as facilities folks, and then many of your past esteemed energy experts, from Jim Sweeney to the Woods and Precourt folks. A lot of folks now at campus that know about this, we do share that. We have these faculty, they're bringing world leaders to see our energy system, like the CEO of Electricity de France and the CEO of Southern Cal Edison. Our energy faculty and staff have access to some of the world leaders and thought leaders on this, and they're bringing them to see the plant and educate them about this. We're testifying at government functions. I personally testified a few years ago when the state wanted to pass a assembly bill to promote more gas-fired cogeneration. I went and testified and say, please don't do that. We don't need more natural gas things. So we do reach out quite a bit.
wonderful. I was wondering if you'd help me.
Sure.
And can we go over here? And I think I probably said it to you a few times. I am painting California's climate plan. And one way to do it, I've looked at each of the 6 goals. I call them sub-goals. And this painting is my attempt. It's a work in progress still. I only have a couple more days and I have to move on to your project. This goal number 2 is to reduce the amount of oil in vehicles by 50% 2030, to squeeze out the oil the transportation industry is using.
Okay.
So this is how I'm articulating it, and this is primarily the impact of, let's say, the beginning of the death, although nothing ever really dies, and building block, energy blocks in cars, you know, gears and other pieces, they are on their way out. So if you're a manufacturer of any of these metal kind of things in the internal combustion engine, and later on, maybe tomorrow, I'm going to put an oil rig off the coast of California, because, you know, that's war trying to put one up there. And I'm going to have the oil come up and come out one of these underground pipelines. And I think it's to say today, if you invest in an offshore oil rig and pipelines, when oil is going to decrease in this state, you're probably going to have a rough time making the money is going to go into the toilet. And I think what's going to happen out there is, this is a car, for example, and the force of you and other people, and to the state, you know, this is very knowledgeable people. We want a good environment. We are going to basically hit the internal combustion engine by where we buy cars and just blow out the engine. That's what this is to depict. You know, we're going to be getting electric cars. We're going to get on high-speed trains. We're going to do a lot of other things. So that's what this articulates. I haven't finished down here, but I want to make the point that coming out of the mufflers of the internal combustion engine is, of course, fumes. And as the cars, more cars out of there is coming barbed wire in effect. And that barbed wire is coming around. Maybe it's part of the planet, whatever. But that barbed wire is having the effect of keeping the heat on the planet, in our environment, whatever. And I tend to think California's climate plan, with respect to decreasing oil consumption by 50%, is we are going to be coming up to where the state is, and they are going to cut this barbed wire. And
I think we already are.
Okay. And heat is going to continue to escape, or at least we're going to decrease the growth of heat. And I have to put this up because we have to make sure people know this is California, not the White House or something, and that's
right
up there. And then you, in this segment or the previous segment, you talked about the electrification that's going on, which is like the digital revolution.
I think so. It's like the digitization of energy.
So I have more work to do over here, and this represents the electrification of everything. And it's hitting what I think of as a sponge, which is the oil in the transportation sector. That's hitting it. And now I'm going to stop because we agreed you're going to ask me some questions.
Sure. So electrification of everything, I think, is the consensus of most scientists that have thought about the problem. And certainly automobiles are a big part of that. How do we convince people that electrification of cars is a good thing? How do we get them to try them out? Because everybody I know, I drive an electric car. Once you've driven one, you say you'll never go back to the internal combustion engine. How do we get that word out? How do we get people to try this?
Yeah, it's not easy. It's not easy. Okay, we have 1 minute left, and I'll just summarize a few things. So I'm making this as like an egg. The state is in it, and being born is the high-speed train that comes up and is going to hit that sponge. Coming out of here is going to be the electric car also being born, hitting it, and this electrification is better. And then there is the arm of the state, which is very powerful. These four factors, the train, electrification, the electric car, and I forgot something else, will have the effect okay, ladies and gentlemen, my guest has been Joe Stagner. I'm Michael Killen. Thank you very much. Make sure you look at, Jim Sweeney's Silicon Valley Energy Summit is June 21. I'll be there. I hope to see you there. We all learn a lot and meet a lot of people. Thank you very much.